North Pole and ends at the South Pole. So now you can see here, magnetic field lines are originating from the North Pole and ending at South Pole. But inside the magnet, the magnetic field lines are from south to north, originating from south inside and ends at north. Second point is magnetic field lines are closer at poles and widely separated at other places. So you can see here in this picture, here these magnetic field lines, this is the pole, na, south pole. So here, see two positions. Compare two position. First position is this. Draw a line like this, and another you can see here. So here, as compared to here, the lines are far apart. So at poles, the magnetic field lines are near. It means that the nearer will be the magnetic field lines, more will be the strength of magnetic field there. So near pole, the strength of the magnetic field is more as compared to any other point which is far from the pole. So two magnetic field lines never intersect each other. Two magnetic field lines never intersect each other. Okay. So Azaan, do you know why two magnetic field lines never intersect each other?
Yes, sir.
Do you know why this is one magnetic field line? Suppose this is another magnetic field line. Why two magnetic field lines can never intersect each other?
Sir, like there will be two directions of the field at the same
Hmm.
point.
Okay. So suppose this is the point now. So you are right. So you will draw a tangent for with respect to this line first. Suppose this is line first. So suppose this will be the direction, first direction of the magnetic field. V1. V1 is representing the direction of the magnetic field for first line. And for the second line, you will draw the tangent like this. So you will get at one point, you will get two direction of magnetic field. You are get suppose this is the magnetic field line. Na? At any point, if you will draw the tangent means you will get the direction of magnetic field at that point. So remember this point. So here you are drawing two tangents and two tangents are in different direction means at this point, at single point, two direction of magnetic field are there, which is not possible. So your answer was right. Hmm. This question is which of the following statements is incorrect regarding the magnetic field lines? So the direction of the magnetic field line at a point is taken to be the direction in which the north pole of a magnet compass uh, in which okay, the direction of the magnetic field at a point is taken to be the direction in which the north pole of a magnet compass needle point. So it is this answer is right. Okay, because I told you that wherever you want to find the direction of the magnetic field, assume there at the north pole and calculate the direction of the total force there, and that direction of the total force will give you the direction of the magnetic field at that point. Magnetic field lines are closed curve, right? If magnetic field lines are parallel and equidistant, they represent zero field strength. No, they are saying that if magnetic field lines are like this, if magnetic field lines are like this, means this is the condition in this region. If the magnetic field lines are like this, means magnetic field is same throughout this region. Means here. At each and every point, the strength of the magnetic field is same. So basically, this option C is not correct. D is saying relative strength of the magnetic field is shown by the degree of closeness of the magnetic field line. More closer magnetic field line, more will be the strength of the magnetic field. Okay, so so this question we will do when we will do the plotting compass. Okay.
Okay.
Huh. After that, these questions we have done. Hmm. So basically, we have done this question. Huh? So this option was correct. Correct means they are asking incorrect. So that is why. Okay, so in this figure, the figure given below shows the magnetic field between the two magnets, magnet 1 and magnet 2. This is the North Pole. Okay, this is the North Pole. They are asking, can you tell me the polarity of this magnet? Hmm?
I don't know.
You don't. Very good. Little, you have to think. You know that we know that magnetic field line. So in case of a bar magnet, this is a bar magnet. Magnetic field line start from the north and end at the south. Hmm? Magnetic field line is starting from the north. Okay. So this concept you will use here and you will get the answer. So this is the North Pole. From here the magnetic field lines are starting. So this will be the South Pole now. So now from here the magnetic field lines are starting. So this will also be the North Pole. And this is the South Pole. Will these magnets repel or attract each other?
Sir,
Hmm?
repel.
Yeah. So in this type of question, you will find in your exam maybe. Okay. You have to apply bit of mind.
Okay.
Because here na, the concept we are using that magnetic field lines are starting from the North Pole outside the magnet. Outside the magnet, they are starting from North Pole and ends at the South Pole. So this is the given condition. So from here, the magnetic field lines are starting and they will make a closed loop and meet at the South Pole, ends at the South Pole. So this will be the North Pole. Okay, so you can define the polarity. So this question is also completed. Now this is the question again. The three diagrams in the following figure show the lines of the force. Lines of the force means the magnetic field lines. Field lines between the poles of a two magnet. Identify poles A, B, C, D, E, F. So now come to this pole A and pole B. This is one pole of a magnet and this is another pole of a magnet. So what I told you magnetic field line always started from the North Pole and ends to the South Pole. So which pole will be A? Hmm?
North Pole.
Yeah, A will be North Pole. Because you can see the direction of the arrow. Magnetic field lines are this magnetic field line starting from this pole. So this pole A will be the North Pole. Same is the case for B. This is also the North Pole. Because magnetic field line is starting. Now for C, tell me for C, which pole C is? South Pole?
Yes, sir.
D is also South Pole because finally the magnetic field line is terminating here. Now this is very easy. E will be North Pole and F will be South Pole. So these types of questions maybe you can get in your exam. So okay. So the next topic is the magnetic effect of current. Magnetic effect of current means due to the current there will be a magnetic field. Hmm? Due to
Yes.
current there is a magnetic field that is known as the magnetic field of current, or you can define in another way. uh, if there is a current and due to the current there is or you can define this in another way. Due to current means electricity, magnetic field means magnetism, so electricity can produces the magnetism. Okay, so a current flowing in a wire produces a magnetic field around it. Okay, and this is called the magnetic effect of current. So is called the is magnetic effect of current. It means electricity produces magnetism. The electric motor, electric generator, this is deleted from your syllabus. Electric motor, electric generator, basically these are working on the magnetic effect of current. what happens there? Due to the current carrying coil rotating in a magnetic field, means there is a in electric generator or electric motor, what happens? A current carrying coil rotates in a magnetic field. Okay, not a current carrying coil, a coil rotates in a magnetic field, and due to that the electricity is generated. So the electric motor, electric generator, telephone, radio all utilizes the magnetic effect of current. All utilizes the magnetic effect of current means they are based on the magnetic effect of current. Okay. So magnetic effect of current is very simple. So now there is one experiment to there we will see due to the current there will be the magnetic field. So this is a plotting compass. So now I am telling you about the compass. This is a in a compass na. This is the compass first. This is south pole. This is the direction of the south pole. This is the direction of the north pole. So this compass has a pointer. This pointer, if there is no magnetic field, so this pointer will face the arrow of this compass will be along north, and the tail of this compass, this compass or this pointer will be along south. So this time this compass is in the neutral position, means there is no magnetic field. If there will be the magnetic field, then this compass will be deflected from this position. Basically, this position you can say is the neutral position, or you can say is the equilibrium position. Okay. So now this is a wire. This is a wire or a conductor, and okay, and this wire na, this wire is connected with a battery. This is the battery. This is a battery. Wire is connected with a battery, and here is a switch. This time this switch is open or closed. The switch is open. So now what you did? You have taken a wire, and that wire you have connected with a battery, and you have placed a compass near the wire. Suddenly you switch on the, means you close this circuit or switch on, you can say. There will be some deflection in the compass. There will be some deflection in the compass. I told you that if there will be deflection in the compass, means that compass is telling that there is some magnetic field around, or there is some magnetic field where the compass is placed. Means you can say that when you will close this circuit or close this switch, there will be the flow of current in this wire, and then what will happen? Due to that current there will be the magnetic field, and due to that magnetic field this compass is getting deflected. There is no other way that this compass can deflect here without any magnetic field. It means that it is proved that due to the current there can be a magnetic field around the magnetic field. In this case you can say if there is a conductor or a wire, if in that wire is, if there is a current, then around that wire there will be a magnetic field. So deflection of compass needle in above experiment shows that an electric current produces a magnetic field around it. Clear? Okay. So now we know that if there is a wire, suppose this is a wire, if there is a wire, suppose, and if in this wire there is a current, so due to that current around this wire there is a magnetic field. There is a magnetic field. This is proved by this experiment. Okay, now this is a straight wire. This is the straight wire. We can take a circular wire. We can take a helical shaped wire, and in that when the current will flow, different magnetic field pattern we will get. So first we will see the magnetic field pattern. Means how is the pattern of the magnetic field? How the magnetic field is distributed? How the strength of the magnetic field is there at different points from the, at different locations from the wire. First we will see for the wire, then we will see for the circular loop. Okay, then we will see for the solenoid. So one by one we will discuss. So magnetic field pattern. by different current carrying conductors of different shapes. So first we will see the magnetic field distribution or magnetic field pattern due to a straight conductor or a straight wire. And after that we will see magnetic field pattern due to a circular loop or circular wire carrying current. And after that we will see the magnetic field due to a solenoid. Hmm? Okay. So magnetic field due to a straight wire. So this is a straight wire AB and current is flowing in that straight wire. So basically concentric circles, these concentric circles are the magnetic field lines. These concentric circles are the magnetic field lines around this wire. So basically magnetic field of the circular wire of the wire, straight wire carrying current will be like this. Will be like this. Current is going in upward direction. So here magnetic field lines around the wire are anti-clockwise. Current is going in this direction, so magnetic field lines are anti-clockwise. These are concentric circles, na? These are concentric circles, and center of these circles is lying on the wire. Here will be the center of the circle. So the magnetic field lines around a straight conductor or wire carrying current are concentric circles whose centers lie on the wire. Now, it has been shown by the experiment. It has been shown by the experiment that magnitude of the magnetic field. Now, magnitude means the strength of the magnetic field. Magnitude of the magnetic field produced by the straight current carrying wire at a given point. For example, this is a straight wire, and in this straight wire, suppose I is the amount of current, and there is a point P which is at a perpendicular distance A. So basically, the magnetic field produced by this current carrying wire is depending upon the distance, inversely proportional to the distance. Means when you will move far from the wire, the strength of the magnetic field will decrease. Okay. And if you will increase the current, then the strength of the magnetic field around the wire will increase. So you can say that magnetic field is directly proportional to the current, and I is the current flowing in the wire. So this is written. So the the magnitude of the magnetic field produced by the straight current carrying wire at a given point is directly proportional to the current passing in the wire and inversely proportional to the distance of that point from the wire. And this is experimentally proven. When you will go in your higher classes in your 12th class, if you have physics, then there also you will study the magnetic effect of current. So this is explained there with the help of Biot-Savart law. So that is not the part of your syllabus. So basically you have to remember these points only. Now direction. Here is the magnetic field now. Around, if in a straight wire there is a current. If in a straight wire there is a current, so there is a magnetic field. So there will be some direction of the magnetic field also, because magnetic field is a vector quantity having magnitude as well as direction. So direction of the magnetic field is given by Maxwell right hand thumb rule. Right hand thumb, what is the right hand thumb rule? Suppose this is a wire, and in this wire the current is going in the upward direction. So what you will do, you will take your right hand, point your thumb in the direction of the current like this, and you will curl your fingers. And the way that you are curling your finger means either you will curl your finger like this or like this. The way that your fingers are encircling will give you the direction of the magnetic field around the wire. So if the current is in the upward direction, so your fingers will be like this. Means anti-clockwise is the direction of the magnetic field lines. Okay, wait, Azaan time is there. So we will wait for 1 minute.
Sir, 2 minutes. I will come back.
Okay. Hello, Azaan. Okay. So, Azan, have you understood the Fleming's right hand rule? Means, suppose if the current is in the downward direction, so what you will do? You will point, you will take your right hand, not left hand, clicking your four fingers will give you the right hand rule. You will get the anti-clockwise direction of magnetic field lines. So you can see the current is in the upward and we are getting the anti-clockwise magnetic field line. If current is in the downward direction, we will get the magnetic field line direction as clockwise direction. Okay, so right hand thumb rule. Imagine that you are grasping or holding the current carrying wire in your right hand so that your thumb points in the direction of the current. Understanding Azan or not?
Yes, sir.
Then the direction in which your fingers encircle the wire will give the direction of the magnetic field lines around the wire. For example, in this direction, if the current is direction of the magnetic field will be anti-clockwise, like this, you will point your thumb in the direction of the current and encircle your finger. Encircling your finger is in anti-clockwise direction. That is why around this wire the magnetic field lines will be anti-clockwise direction. If the current is going in the downward direction, then direction of the magnetic field will be clockwise direction, like this. Okay. Azaan, please you should take the screenshot, okay, from here.
Okay, sir.
Yeah, magnetic from here. Okay, so um, just a minute. Azaan, just wait for a minute. I have a call.
Okay, sir.
Okay, Azaan. So now, Azaan, please take the screenshot of this.
Done, sir.
Then okay. Okay, please take this screenshot. Done, Azaan?
Yes, sir.
Okay. So this is the experiment that is showing that due to the current carrying wire, there is a magnetic field. Okay. After that, you can take the screenshot of this. Done?
Yes.
Okay. So now you should take the screenshot of this. Done, Azaan?
Yes, sir.
Okay, so please take this one. This is screenshot. When you have taken took when you took the screenshot, you can inform.
Done.
Done?
No, sir. Once. Done, sir.
Scroll down.
Yes.
Okay, so you know this when current is going in upward direction, so direction of magnetic field will be anti-clockwise, downward, clockwise. Okay, so after this, Adhan, actually there is a requirement of a class of at least 40 minutes more. So will you join tomorrow for completing the syllabus? Means
Yes.
I am saying that for completing the whole syllabus means this chapter, there's a requirement of one more class, and that of 40 minutes, and I will finish the syllabus in that. Okay. So the next topic we will discuss in the next class because here I have to explain something. Uh, and okay, so please join the tomorrow's class so that we can finish the all whole syllabus. Whole syllabus means there are remaining few topics more are there that we can finish in 40 to 50 minutes. We can finish two topics. So how was your pre-board exams?
Good.
Okay. So, and in maths, how what is the status in mathematics?
Sir, maths was good too.
Good, no? So, are you practicing the questions? Hmm? Actually, we have not
Yes.
completed in with me. You have not completed all the chapters, but I am hoping that in your school you did that.
Yes, sir. Yes.
Okay, because you were absent from so many classes, so that is why we are not able to do that. But you have already completed that, so you should revise. And revision, the way of revision should be by writing in
Yes,
mathematics,
sir.
by solving the question, and practice more and more question in maths. And in physics, you can go with the notes that I have given from the light